What's up, scholars? Today we're talking about graphing trig functions part 2. So as you can see, we're on Desmos right now, and I want to show you how to graph trig functions and change the axes on Desmos and add those sliders that we saw in our video from last time. So let's say we want to talk about f of x equals, we had our a for amplitude, sine, and then we had b for period, so bx plus c, and it's going to give us an option to add all of those sliders. So that part is pretty easy. Now let's go over here to the graph settings. Let's change our x-axis to be in terms of radians, which means we're going to go with the pies. So 2 pi would be a circle. So maybe we'll go to negative 4 pi. Give us a little bit more here. Go 4 pi. And let's say our step, let's do every 45 degrees or every pi over 4. Okay, cool. And then we know that in the standard version of our trig function, looks like, what did I do here? Our amplitude is 1, our period coefficient there is 1. Right now we've got a plus c of 1, that's why it is up there. If we go down to 0, there we go. There's our normal little dude here. Normal little dude. Great. Yep. The amplitude being 1, I don't have to go all the way up to 6. We could make this, well, it's a square graph. It's okay. I feel like it's fine. You could change this, so you could change your y-axis to be a little bit less. Let's say we did negative 4 to 4, and then we'll zoom in just a little bit there. And then you can see we've got radians clicked here. All right, cool. So if we get out of our settings now, if we zoom in and out, we'll see all the pies here on our axis. Very cool. And there's our pi over 4, those are 45 degrees, pi over 2, 90 degrees, pi 180, and such and such and such. And now you've got these sliders that you can play with. Whee! So changing the amplitude, making it smaller and larger. Whoa, what happened here? So last time we talked about how we never consider the amplitude to be negative because it's a distance and distances aren't negative. But what is happening when the a value becomes negative? Can we see here? Right now, it's going up like this and down. And then when we switch and we go negative, boom, we've changed the concavity. Changed the concavity. What happened? Why did it do that? Why, when we are in the negative, is it all of a sudden flipped? Well, remember when we talked about transformations before, when you have a negative value outside the front, we are flipping over the x-axis. That's what happened here. So our negative values for a, again, the amplitude itself is not negative, but we've got a negative in front of our amplitude here. So this amplitude, if I have it set at -3, I guess I can get rid of these little goofy things now. If we had our amplitude at -3, the amplitude itself would be 3, but the negative there is what flips it over the x-axis, so that as we cross through 0, we are no longer going up like we did before. Now we're going down. That's because we have an x-axis flip across the x-axis here with that negative value. So that's how we play with our sliders. We just add in the letters here, and Desmos will automatically give us an option to add sliders. What happened with the 0? Why did that occur? Oh, because I changed this whole thing to be f of x equals 0, essentially, plus my c here was 0. So now this is a flat line that could move up and down with the c. But that's not very fun. Let's give ourselves, there she is. Nicely done. So the c changes up and down. And our B changes our frequency of oscillation. So as we saw before, higher and higher values are going to change so that we have more and more oscillations per time. Ooh. And low numbers. Wait, what happened again? What do we do there? Low numbers of B, like negative numbers of B. Where did that go? See, that had another flip. Yep. Now we're not going to be super concerned with negative values of B. We will see in our work today some negative values of A, where we're just looking for the flip across the x-axis so that at the 0 point, we're starting to go down instead of our traditional up, like on a sine wave. All right, let's go play some delta math, guys. All right, so for this little bundle of joy, we're going to write an equation of the trig graph that we see below. So again, this value is going to be our amplitude. Right, that's our A value. This guy is going to change our period. And this guy is going to be our C, our plus C. That'll change our position up and down on the graph. Okay, so we're taking the solid line here and trying to match it with the dotted line here. And we see that they have the same period. They have the same oscillation. The period being 2 pi. So we don't need to change that. Let's just put a 1 in here. It also looks like, what's the amplitude of this? Of the dotted line? Well, the top shows up at 5. The bottom would be at 4. So 5, or sorry, not 4, 3. 5 minus 3. 5 minus 3 is 2. Divided by 2 is 1. So the amplitude is still 1, which means the only thing that really happened here is that we shifted. Now, where is our midline? Our midline's not at 5. It's not at 5 here. The midline would be at 4. Actually, just for funsies, let's see what happens if I tried 5. Oh, too tall, right? So we want our midline. That's our plus C here is our midline. I noticed this is a cosine graph. This is a cosine graph because it started, and by started, it had a y-intercept on its highest position, as where sine has its y-intercept in its midline. So there we go. That's how we write an equation of this trig graph here. Let's do another one. All right, so we've got our solid line, which is a cosine graph. We've got our dotted line, which is still going to be cosine. We're never going to switch from sine to cosine. That's not what's happening here. So let's check out our period first, our frequency of oscillation. So if we start, I'm looking at the solid line here. It's y-intercept at 1, goes down, comes back up to 1 at 2 pi. So our dotted line starting up here at 3, goes down, comes back up at 2 pi. All right, great. So the period is still the same. We're still going to have a 1 in there. The amplitude of the dotted line, what's tallest tall would be at 3, lowest low at -3. So if we did 3 minus -3 divided by 2, 3 minus -3 would be like 3 plus 3 divided by 2. 3 plus 3 is 6 divided by 2 is 3. So our amplitude is 3, which puts our midline still at 0, right? Because our amplitude is 3, from 0 and down 0, our midline should be at 0. Let's give it a try. Oh, love it. That's so satisfying. I think let's do one more. I'm just having a good time. Okay, another cosine graph. Here we go. Let's check out our period again. So the traditional cosine graph has a period of 2 pi. Now, this dotted line graph, if I look at where it starts at 0, 0 here, it goes up and comes back down at 2 pi. Okay, great. The period is the same. Fabulous. Let's find our amplitude. The highest high of the dotted line is 4, lowest low is 0. 4 minus 0 would be 4 divided by 2. That's our amplitude, would be 2, which puts our midline at 2. Now let's try, see what we get. Huh, what happened here? It's like it flipped. It's like it flipped right across its middle. How did we do that when we were on Desmos? I think, did we put a minus there? Yes, we did. That is exactly what happened. We needed it to flip, so we put a minus out in the very front. Awesome. Yeah, Desmos, give me some points. All right, great job, guys. That is how we do some trig graph discovery level 2. All right, let's check out this next one where we are writing trig functions given features. So this says, write a cosine function that has an amplitude of 2, a midline of 4, and a period of 5 pi over 8. What? That's okay. We can handle this. We absolutely can handle this. So what was the function, the general function that we used? We said f of x, right, again, it should be f of theta, equals a for our amplitude. In this case, we're going to be doing cosine of bx, where the b is going to help us out with the period, and c is going to be our midline, right? A for amplitude, b for period, and c for midline. Remember, the period is actually 2 pi divided by b. So all these previous problems, we were putting a 1 in there because the period was 2 pi. So we were doing 2 pi divided by 1, which is 2 pi. So in this case, where we have a period of 5 pi over 8, we're actually going to have to solve for b. But we can do that. Not a problem. Not a problem at all. So in this case, our period is 5 pi over 8. 5 pi over 8. So let's set that equal to our 2 pi divided by b. And we're going to solve this equation for b. For pre-calc scholars, not going to be a problem. We see a fraction equaling a fraction. Let's just do some cross multiplying, shall we? Oh yeah, here we go. So 5 pi times b. We don't know what b is, so that's just going to stay as a variable. So we've got 5 pi b equals 8 times 2 pi. 8 times 2 is 16. Let's divide by pi. We see right now there's a pi on both sides. That can be, that can go away. We can divide by pi on both sides, and that can go away. We can also divide by 5 on both sides to get the b by itself. So we divided by pi on both sides. I just did that real quick, crossed it out. Now we're dividing by 5 on both sides, so we're going to get that our b is 16 over 5. Not a nice round number, but it's not a problem. It's all good. So the b number that we're putting in here into our equation is going to be 16 over 5. Our amplitude is 2 cosine 16 divided by 5. We still have our x in there. That comes after, right? So we just solved for b. Don't forget about our x. And we've got close parentheses plus our midline of 4. Submit our answer. What you got, Desmos? What you, or not Desmos, Delta Math. Tell us we're correct, which of course we are, because we're a bunch of geniuses. All right, let's do another one of these. Another cosine function that has a midline of 5, an amplitude of 4, and a period of pi. So let's keep this guy, our function dude. Let's erase all this so we can solve for another one. Here we go. This one, midline of 5, amplitude of 4, and a period of pi. So really all we're solving for here is the period, because the amplitude is just going to go smack in the front, midline going to go in the back. So in this case, our period is a pi. So pi equals 2 pi over b. We could solve this the same way if we made the pi a fraction, which we would do by over 1. Et voila. Then we cross multiply, we do b times pi, which will be pi b, or b pi. Either one seems kind of strange. Pi b, let's do that. Equals 1 times 2 pi, which of course is 2 pi. So let's get that b by itself by dividing by pi. Dividing by pi. So in this case, b equals 2. Not too bad. What do we say? Amplitude of 4. This is a cosine. Our b is 2. Again, we still have our x, parentheses, plus midline of 5. Can-do'sville. You know what? I'm feeling saucy. Let's do one more. Ooh, now we're into a sine function this time. Does that change anything? Not in the slightest, because this is still our general formula. Oh man, I lost my little guy. There we go. Still be our general formula. We'll just remember to write sine this time instead of cosine. So this sine function has a midline of 4, amplitude of 5, and a period of 2. Ooh, we can still do this. I changed this into a type of question you're not going to have, where it has a period that doesn't have pi. But for proof of concept, it's the same idea. Period is 2, so 2 pi over b. Solving this for b, let's make this 2 over 1. So b times 2 would be 2b, or not. Haha, get it? Got it. 1 times 2 pi is 2 pi. Divide by 2 on both sides. Divide by 2 on both sides. So in this case, b would equal pi. B would equal pi. It's the same idea, just now it's pi instead of a number. So we would say we're doing a sine function here. It's got an amplitude of 5. So 5 times sine of our b is pi. So let's plop that in there. X plus, oh, too many parentheses now. So many parentheses. Plus our midline of 4. Submit our answer. Very good. Awesome. Nicely done, scholars. We talked about writing trig functions from given values. We talked about matching graphs, and we talked about how to put all this good stuff in the Desmos so you can play around with it. Gosh, it's nice. Truly delightful. We talked about when a is negative, there's a negative in front of your amplitude. It switches the function across the x-axis. We have an x-axis flip. Again, the amplitude itself is still a positive number because it's a distance, and a distance is a positive number, but the graph itself, it does flip. Them's are the rules of graphing. Negatives out in front of the function are an x-axis flip. All right. Love you so much, scholars. Take care of yourselves. See you next time. Keep on that hustle.